Hi, everyone. Thank you so much for joining us. We're going to give it just a minute while people filter in, and then we will get started with the presentation. If you're just joining, thank you so much for tuning in for today's presentation. We're just giving it 1 minute while people filter in, and then we will get started shortly. All right, looks like we've got a pretty good mass of people, so I'm going to kick things off. Thank you all so much for joining us today. I'm Gwen Brown. I'm IREC's Vice President of Communications, and I'm going to provide a little bit of background to kick off today's webinar, and then I will hand it over to my colleagues on IREC's regulatory team to deliver the substance of today's presentation. Today's session, Deconstructing Direct Transfer TRIP, will explore research findings from a recent report by the Interstate Renewable Energy Council of the same name. Direct Transfer TRIP, or DTT, is a grid protection strategy that some utilities require as a condition of interconnecting distributed energy resources, or DERs, like storage and solar, to the grid. DTT is one way of addressing the risk of unintentional islanding, which can occur when a segment of the electric grid remains energized by a DER after being electrically isolated from the rest of the grid. And it can present safety and reliability risks. However, DTT is highly contentious because of its exorbitant costs, which can make projects, and in some cases, whole clean energy programs, infeasible. The report that we're presenting today evaluates the various utility justifications for requiring DTT, analyzes the risk of unintentional islanding and other justifications, and outlines a suite of alternative strategies that can effectively address grid safety and reliability concerns for inverter DERs. If you are not yet familiar with our organization, IREC is an independent 501c3 nonprofit that builds the foundation for the rapid adoption of clean energy and energy efficiency to benefit people, the economy, and our planet. And we do that through 3 interconnected programs that address some of the critical requirements for clean energy to grow: a robust and well-trained workforce, sound energy regulations, and supportive local policies like permitting and zoning. And you can learn about each of those programs on our website, irecusa.org. Today's presentation is brought to you by IREC's regulatory team, which helps US states and territories regulate their electric utilities to ensure distributed energy resources can rapidly and equitably decarbonize the grid. Our regulatory team focuses on 5 areas of specialization to ensure that utility regulation enables equitable clean energy development while maintaining safety, reliability, and affordability. And you can see those 5 areas here. Smart DER siting focuses on tools that help inform where DERs can be developed without the need for costly and time-intensive grid upgrades. Our innovative DER integration program focuses on technical solutions to enable our existing grid infrastructure to accommodate higher levels of renewables. Rapid utility approval focuses on improving utility regulations and processes, especially interconnection rules. We also work on utility accountability to ensure that both that utilities are applying sound approaches and that they are complying with the regulations that govern them. And the research that we are presenting today on direct transfer TRIP falls into that category as it assesses justifications that utilities are using to require an extremely cost-intensive solution. And finally, our clean and equitable grid work helps ensure that distribution planning, grid investments, and interconnection processes don't create undue barriers to clean energy access for specific groups. Today's presenters and the authors of the report that we'll be discussing are Brian Leidick, Ray Walling, and Shay Banton. Brian Leidick is IREC's Chief Regulatory Engineer. He's been active in renewable energy since 2005, starting out in installation and then working on standards and regulatory issues for PV inverter manufacturer Fronius. He's been with IREC since 2017, where he works with regulatory stakeholders to increase access to sustainable energy and energy efficiency. He's a member of UL 1741 and IEEE 1547 working groups, and is a founding member of the Forum on Inverter Grid Integration Issues, or FIGI. Ray Walling is the president and principal of Walling Energy Systems Consulting, LLC, where he's engaged in a diverse range of transmission, distribution, renewable energy, and distributed generation technologies and issues, serving utility, government, power plant developer, and research institution clients. Shay Banton is an energy systems engineer, grid integration policy expert, and energy justice advocate with 8 years of experience spanning utility regulation, clean energy development, and federally funded R&D. Their work bridges engineering and equity to drive just, accountable, and inclusive clean energy policies that center frontline and historically marginalized communities. Shay has shaped foundational interconnection reforms in multiple states and helped launch the U.S. Department of Energy's National I2X initiative to improve interconnection practices nationwide. Before I turn things over to our expert presenters, just a few logistical notes. First, if you have any questions as we are presenting, please submit them using the Q&A box in the control panel at the bottom of your screen. You can add your questions at any time, and we will address as many of them as we can at the end of the presentation. And I want to highlight that if you're interested in hearing the answer to someone else's question, there is a thumbs up icon that you can use to upvote a question. And we will prioritize the questions with the most interest at the end of today's presentation. The chat box is disabled, but if you have a technical issue, you can also note that in the Q&A and one of our staff will follow up with you. We do have closed captioning if that's a feature that you need. You can select show caption from the control panel at the bottom of the screen. We're not accepting AI note takers or bots in our webinars, but we will be providing the slides, the recording of today's presentation, and other resources in the next few days after the presentation. And now I am thrilled to turn things over to Shay Banton to get into the substance of today's presentation. Take it away, Shay.
Thank you so much, Gwen, and so excited to be here with you all today to present on this particular report. So deconstructing direct transfer trip, a really complicated topic, and we were really excited to tell you about our findings. We're going to actually go to the next slide, the agenda slide. So again, we're excited to talk to you about some of the key findings from this latest report. A quick heads up that because of time constraints, we won't dive into every technical detail behind the findings. So if you're curious about the nitty-gritty, we definitely recommend you read the full report when you get a chance. So here's a quick look at what we're going to talk about today. First, I'll start by level setting with a brief overview of what direct transfer trip is and how it's used. Then I'll introduce the results of our critical review of various utility justifications given for requiring DTT. After that, Ray and Brian will walk us through the main thrust of our paper, quantifying the risk of unintentional islanding by DERs. And then Brian will give us an overview of the screens currently deployed to assess UI risk, followed by a summary of our report's key findings. Next slide, please. So diving right in, what even is direct transfer trip in the end of the day? So at its core, direct transfer trip is a communications-based protection method. It uses direct point-to-point communications between geographically separated equipment to accomplish a specific protection objective. And when applied to distributed energy resources, DTT's primary function is to quickly disconnect DERs, stopping them from generating after being electrically isolated from the grid. Here's how it works. First, a fault or switching event occurs, isolating a line segment that includes both loads and DERs. Next, an upstream protection device senses the fault and responds by opening a breaker, isolating the segment and stopping the flow of fault current. And finally, the trip signal is transferred to protection devices at downstream DERs, triggering their disconnection and preventing them from creating an unintentional island. These strip signals can be sent via various communication channels, but the most common is fiber optic cable. And while it's incredibly reliable, it is also, actually and also really, really expensive. And that cost can push projects or even entire solar and storage programs beyond the point of financial viability. One final note before we move on. Throughout the report, we regularly distinguish between types of DERs, such as inverters and rotating machines. While both generate power, their behavior during faults and islanding events is very different, and that difference matters in how they should be treated in screening and UI mitigation. More on this later. Next slide, please. So now that we've got a handle on what DTT is and how it works, let's examine some of the rationales used to justify its deployment. Next slide. Starting with the most common justification, public and worker safety. The concern is ultimately if a power line goes down, say from a storm or car accident, and DRs keep generating, they could energize that line and pose an electrocution risk. Now, IREC fully agrees safety is non-negotiable in grid management, but the justification has to match the risk. And here, the evidence tells a different story. First is that the risk from live conductors already exists, such as for high impedance faults, and is handled through standard utility practices. Second, research shows that DERs don't significantly add to those risks and can be properly managed in other ways. And third, the odds of a worker actually encountering a DER sustained island while doing maintenance are near zero. So yes, safety matters, but inverter DERs do not meaningfully increase electrocution risk, and that alone does not justify requiring DTT. Next up is protection miscoordination. This refers to the possibility that DERs might respond more slowly to faults than utility equipment, resulting in various problems. This includes out-of-phase reclosing, where a utility auto-reclose scheme used to quickly restore service to customers closes back into a line before DERs disconnect. This results in phase mismatch. However, our research shows that inverter DERs respond quickly to faults, making this scenario extremely rare. And even if there were a concern, solutions like extending reclosing intervals or using voltage supervised reclosing are far more practical than requiring DTT. There's also worry about nuisance tripping, where high DER fault currents improperly activate protection devices. However, unlike rotating DERs, inverters do not have high enough fault current to cause such misoperation. The bottom line is that miscoordination is not a valid justification for requiring DTT for inverter DERs. Next slide, please. Another concern highlighted is that customers may be exposed to unacceptable power quality deviations that could damage equipment during an island. However, these concerns ignore a few important points. A. Inverters are required to quickly cease exporting if voltage or frequency drift outside tight limits, such as 88 to 110% of nominal voltage. B. That even if an island lasts longer than 2 seconds, it can only persist if grid conditions remain within those narrow limits. And C. It is well established that loads are designed to withstand such deviations for limited durations. So between the short islanding duration and built-in protection triggers, the actual risk to customer equipment is very low. Again, such concerns do not justify DTT. And lastly, we've seen a handful of less technically grounded arguments that we feel obligated to address. First are references to the Odessa disturbance event, in which transmission-connected DERs failed to ride through a grid disturbance. This is used as generalizable evidence of inverter unreliability that only DTT can address. However, this event was entirely unrelated to both unintentional islanding and distribution level interconnection, and ultimately has no merit in justifying DTT. Second is a common over-reliance on limited anecdotal examples of inverter operational failures as justification. Such decisions discount highly collaborative standards development efforts and robust testing procedures, especially for certified inverters. Third are unsubstantiated claims that inverter DERs elevate wildfire risk, while research actually shows that these systems are crucial for climate adaptation and resilience. Lastly, that subtransmission ground fault over voltage protection requires the use of direct to DER direct transfer trip. However, there are equally reliable and more cost-effective alternatives that can be deployed. Ultimately, when critically evaluated, none of these arguments hold up a solid justification for requiring DTT for inverter DERs. And with that, I'll pass the torch over to Ray Walling, who will walk us through how we've quantified the risk of unintentional islanding in our report.
Thank you, Shay. I'm going to be talking about risk and risk assessment, and so we really need to quantify that risk. It's really not possible to have absolutely zero risk. For example, there's always a finite risk that if you step outside, you might get hit in the head by an ice ball falling from the airliner having a leaking lavatory drain. I mean, things can happen. So you really have to balance the risk with the impacts of risk avoidance. And if you never went outside, you get pretty hungry unless you started becoming totally reliant on Grubhub. So we need to keep things in perspective and have an understanding of the quantitative risk of a DER energized island persisting to really evaluate the need for DTT. Okay, so when can an unintentional island occur? First of all, um, a persistent island requires three basic situations to exist simultaneously. You have to have a reason that the utility feeder circuit is opened in the first place and separated from the greater power grid. And this reason is closely tied to the other situations that we'll be talking about. Second of all, you need to have a balance between both the active and reactive power uh, balance between generation and load simultaneously. And this is often overlooked, the fact that reactive power balance is far more important than active power or real power balance. And then third, the you can't have a disruption of the source of the DER. In other words, if the initial islanding is caused by a fault and the fault creates voltages that causes the DER to trip, then there can no longer be an island. And so we're going to talk about these things in detail. So basically, the DER are required to trip off whenever voltage or frequency of the island goes outside of a defined range. And that's very likely to occur. And we'll be talking about each of these points in further detail. So first of all, let's talk about the opening of a power grid circuit. Uh, by, by far, the vast majority of utility feeder circuit openings are a result of short circuit faults that are detected by a utility protection system. And the latter part is important because if the fault is such a high impedance that it can't be detected, then it's not going to cause the utility circuit to trip. So in most cases, these faults are left on the circuit that becomes disconnected. And short circuit faults, once they occur, generally don't go away unless all energization is removed. So this means that if a fault causes a feeder circuit to be opened or tripped, the potential island will be left with a short circuit, which is likely to cause voltages to be pulled down to the extent that the DER will immediately trip, particularly inverter DER, which does not have much strength to hold the voltage up in the case of a fault. Much less frequently, a distribution circuit could be tripped due to a fault upstream of the feeder, such as on the substation bus. But while the fault in this case is not left on the islanded feeder, the fact that you had the fault, which did pull the voltage down on the feeder, and then the fault goes away, you're going to have a big inrush of current into transformers and into motors as they reaccelerate on the circuit, which creates a big transient and is very likely to destabilize an island and not allow the island to persist. Okay, the last possibility then is some kind of a manual switching event that isolates the feeder. And utilities are measured by their regulatory commissions on customer reliability. It is very rare that a distribution circuit is intentionally switched off because doing so creates a reportable outage. Therefore, utilities go to great lengths to avoid intentional circuit turnoffs, such as performing almost all line work hot, even to the extent of replacing the actual line conductors themselves hot. Uh, in a rather complicated process. Circuits could also be potentially shut off accidentally, but this is avoidable by the use of well-accepted switching practices, switching clearances, and so forth. As I mentioned before, we have to have a very tight balance of generation and consumption of both active and reactive power on the island in order for the island to remain stable. Any mismatch results in frequency or voltage deviating from normal, and with too much deviation, the mandatory tripping of DERs will occur, ending any chance of an island. With an inverter energized DER, the active or real power mismatch determines the voltage magnitude, and the reactive power mismatch determines frequency. This is opposite of what happens with conventional rotating generators, and this is a point that often confuses many engineers. So the range of mismatch, essentially the real and reactive power flow through the switch that isolates the circuit before it is opened, for which the frequency and voltage do not result in immediate DER tripping, is called the passive non-detection zone. In other words, if the mismatch is tight enough, then there's the DER won't trip naturally. It can still trip due to the active anti-islanding algorithms, which are essentially required by UL 1741 and IEEE 1547. But the natural behavior will automatically take DER off if the power mismatch is outside of this relatively narrow range we call the passive non-detection zone. And so mismatch outside of the zone makes an island impossible, independent of any anti-islanding features. It is simply the natural circuit behavior combined with mandatory DER frequency and voltage tripping that terminates any island very quickly that's outside of this narrow PNDZ. And because reactive power mismatch determines frequency in the case of inverters, and over and under frequency trip levels are much tighter and specify a much narrower range of operation compared with voltage trip levels, the reactive power balance is far more critical for the persistence of an island than the real or active power balance. The Electric Power Research Institute, or EPRI, has developed a software tool called IPRAT, or Islanding Probability and Risk Assessment Tool, that uses a year-long time series of distribution feeder load and PV output profiles to determine how much time over the year a typical feeder operates within this PNDZ. If we look at the figure on the left, we can see that even with PV capacity equal to the distribution circuit's peak load, not minimum load, but peak load, the probability that a feeder disconnection can possibly result in an island is on the order of 2 to 5/100ths%, depending on what's called the quality factor of the circuit. And quality factor is a metric of how robust the circuit is to frequency variation, and it is effectively governed by the amount of shunt capacitance connected to the islanded circuit. If you don't have shunt capacitors on the circuit, there's like very little chance of ever having an island whatsoever. So this means there's basically about 1 chance in 2,000 to 5,000 that an island might persist if the circuit was dropped without a fault and all the inverter anti-islanding functions do not work. The figure on the right shows how exact the reactive power match must be between the reactive power generated by capacitors and DER compared with the reactive power demanded by loads and system reactive power losses. For the more typical case of the circuit quality factor being around 0.3, the pre-trip power factor of the circuit would have to be between 99.95% power factor leading to 99.95% lagging. In other words, almost perfectly fully compensated and no more for any chance for there to be any chance of an islanding even forming. Okay, also the third element, the third ingredient is that it has to be no disruption to the island. And as I mentioned previously, almost all feeder drops are caused by a fault. And so while large rotating generators can potentially support the system voltage during fault such that the DER does not trip due to the resulting voltage, inverter DER are a weak constant current source. Faults must have an impedance small enough for the utility protection to detect in order for the feeder to be tripped. And given that constraint, a fault will either cause an inverter DER connected to the feeder to trip or cease energization in a small fraction of a second, either due to the resulting undervoltage on the faulted phase or overvoltage on unfaulted phase. This is true for all but the most extreme examples of distribution circuit topology. Other disruptions to an island are the result of anti-islanding algorithms required to be implemented in certified DER. So the question is, given these predictions and assuming anti-islanding is ineffective, what is the probability that an inverter DER-induced persistent island will occur for a particular circuit? And using the EPRI-IPRAT tool and working through and assuming that that a feeder might be manually or dropped without a fault on the order maybe once every 5 years, and that's even a lot. That the chance of an island is something that's once in every between 3,800 years to 10,000 years in terms of mean time to recurrence. So I'm going to be now turning this over to Brian, who will take this discussion further.
Thank you, Ray. And I'm seeing my, there I am. All right. Hopefully you can hear me okay. So there's been a lot of discussions over the years where utilities and others have raised concerns about active anti-islanding that's in the inverters maintaining its effectiveness in the real world. And three prevalent issues have really been discussed that we now have research addressing for each of these, which is when the advanced grid support functions are enabled in inverters and whether that could help balance the island or not. When you have multiple inverter scenarios, different kinds of manufacturers that have different, potentially different active anti-islanding methods playing against each other on the same circuit, as well as circuits that have both inverters and rotating generators. In the first one, dealing with advanced grid support functions, there have been extensive tests by Sandia and EPRI that have shown those support functions not to really be an issue in terms of stabilizing an intentional island. And in fact, they can have the opposite effect in terms of increasing, and depending on the level of penetration and whatnot, they can potentially, in some cases, actually decrease the island detection times. And one reason that may be, if you think of the example of the volt-var function where the inverter increases VARs dependent on voltage, in an island, the inverter has basically an inverse relationship between active power and reactive power and frequency and voltage. So in the island, if you increase reactive power, you're actually coupled, the reactive power is coupled to frequency. And so you're not going to balance the voltage by utilizing VARs. You're actually just likely to change the frequency, which might send you to a frequency trip point, or at least not interfere with your anti-islanding algorithm. And at any rate, so that's been shown through the research to be true, and that, you know, the in all the cases that have been tested, they maintain their active anti-islanding detection time within 2 seconds as required by the standard with all the different combinations of grid support functions. And any inverter, which is pretty much all of them that are UL 1741 SB certified, those are tested for anti-islanding with those different combinations of grid support functions enabled to ensure those anti-islanding algorithms are still compatible. The next one that's been worried about is that inverters having different anti-islanding methods could potentially play against each other and desensitize each other's anti-islanding or desensitize the anti-islanding as a whole of the circuit. And Sandia has also done testing within the last several years that's found there is some merit in that concern, but they also found that the most common anti-islanding methods that are based on frequency, which are similar to or known as the Sandia frequency shift, that's been around for quite a while, they still work well when they make up the majority of the island. And those are referred to in the literature, in the Sandia literature, as group 1 or 2A methods. And just note that EPRI and IEEE 1547.2 added some methods and the numbering changed a little bit. But when enough of those types of anti-islanding methods are present, generally if they make up at least 50% of the island, then they make up for the less effective methods that might be present in the island. So the less effective methods might actually get tripped up by other methods, but these methods are generally effective and make up for the lack of effectiveness for those other types of methods. And then we can basically apply this knowledge to screening criteria that could be used to determine the percentage of anti-islanding methods in a circuit. And we'll talk a little bit more about those potential screening practices later on. It's also been long known that rotating machines can impact anti-islanding effectiveness. And the Sandia 2012 island screening methodology that's been relied on for a long time noted that rotating machines making up greater than, say, 25% of the island could stabilize the island and cause anti-islanding to fail. So that's been a potential screening practice for quite a while now. The Sandia research the same research that looked at the multiple inverter scenario also looked at combinations of different anti-islanding types and rotating generators in various percentages and found that the highly effective types that I mentioned can also detect islands with up to around 40% penetration of rotating generators in the circuit. So this again can be used as a screening method, as it might already be done today when rotating machines are present. And it should be noted that rotating generators often already have direct transfer trip applied, meaning they would not make up a part of the unintentional island. And that is, we certainly encourage that because rotating machines certainly can support an island and would generally only have passive trips outside, and they don't contain active anti-islanding methods themselves, so they actually need some sort of communicated anti-islanding method applied. But since they generally already have DTT, you're unlikely to get into a scenario where you have a large percentage of rotating machines mixed with inverters, and that those rotating machines don't already have DTT in place. As long as they have DTT in place, then they're not going to affect the inverter's anti-island effectiveness when the island begins and the DTT trips the rotating machines. So moving on to something called ground fault overvoltage, which can occur during switching. Doesn't necessarily need a persistent island to cause an overvoltage, but this is one potential effect of islanding that has been of interest, and DTT has been applied to avoid ground fault overvoltage. But there's some potential misunderstanding between how rotating machine generators in the past have worked versus inverters. So most distribution faults involve a short circuit from a single phase to ground. And in a distribution circuit that has a significant rotating generator DER, that can cause what's known as ground fault overvoltage. That's typically an issue for 4-wire grounded distribution systems. And we'll just talk a little bit about what that means. So the way this can happen is first the fault occurs, And notice the three-phase representation on the right there now has an additional ground point in the lower right phase. So both the utility and rotating generators start to feed the fault, and then the utility protection opens, isolating the circuit. And without the proper ground source on the isolated circuit, the generators enforce the phase voltage and cause the normal phase-to-phase voltage to be applied to the non-faulted phases. So you can have an overvoltage of upwards around 173%. So that can be damaging to utility and customer load equipment. And the situation has driven utilities to specify effective grounding, as it's called, of DER, which is wise, especially in the case of rotating generators. But the idea of effective grounding has been potentially misapplied to inverters. And when that's done, it's often accomplished by the addition of a grounding transformer or a grounding bank. So what about inverter DERs? It's not necessarily true that inverter DERs are going to cause ground fault overvoltage in this single line to ground fault scenario. And since they behave differently within the island than rotating machines do. So inverters are a constant current source and not constant voltage source like a rotating generator. And if an inverter injects 1 per unit current into a grounded load having 1 per unit impedance, then the phase to ground voltage is going to be 1 per unit, regardless of the DER being effectively grounded in the traditional sense or rotating generator sense, meaning that you don't have any change in voltage. So the circuit in this case is actually grounded by the load, and that is different than the scenario with the rotating machine. And in a typical 4-wire distribution system, the large majority of residential and small commercial load is grounded, and large commercial load is mixed. And it's been found, and we show in the report, that 1/3 of the island's circuit load needs to be grounded for the circuit to be considered effectively grounded in the inverter case. As you can see here in case 3, where the unfaulted phase to ground voltages are 80% of the line-to-line magnitude or 138% of nominal, which is the definition of effective grounding per IEEE C6292.1. So there's widely applied rules of thumb used by utility industry to specify grounding banks for DER. And these are typically based on rotating machine generator characteristics that are not particularly the best for inverter DER. And case 6 shows that a much smaller grounding bank with a neutral grounding resistor instead of a reactor does much better than those typically specified based on the understanding of rotating machines, as you would see in case 5. Where the overvoltage is actually higher. And when you have 100% of the load, or 100% of the load in the island is grounded, then grounding transformers with the parameters specified similarly to rotating machines can actually cause higher voltage than if there was no grounding bank at all. So ground fault overvoltage is generally mitigated by existing load, but most utility practices have not applied that learning and continue to require over-specified grounding banks. Now I'll chat a bit about existing screening practices for unintentional islands. So there's a wide range of screening practices across the country, ranging from simple penetration screens to more complex screening that looks at the other characteristics and applies mitigations such as DTT or voltage supervised reclose blocking when screens are failed. And I'm sorry to throw out a bunch of terms here. If you read the report, you'll understand better what those mean if you don't already. But more of these practices today whittle down the scenarios where DTT is applied and may offer a detailed risk of islanding study before determining the need for DTT. But still, older simplistic practices exist where they're just going on a simple penetration screen of active power. But those risk of islanding studies that I mentioned, those can be expensive, so it's best to avoid them if they're not necessary. But they're also generally more palatable for developers than the application of DTT if they can find through the risk of islanding study that DTT is unnecessary or that there's no risk of anti-islanding failing. But some utilities have started to integrate screening for the anti-islanding groups that I mentioned earlier to ensure that their effectiveness is maintained with the multiple inverter scenarios and with rotating machines in the circuit. However, no screening that we know of is based on reactive power, which Ray showed is the main driver of a potential island balance characteristics. And they all rely on that active or real power balance. So we think further improvements can be made. And so generally across the country, there's this range of just very simple screening practices to more progressive and complex that whittle out a lot of projects before they potentially apply any mitigations. Excuse me. Now, summarizing the key findings here. One of the big takeaways, with the help of the analysis Ray went over, is the level of actual risk of encountering an island. So first, for inverter-induced islands to form, a manual switching event must occur, which is only likely to happen, as Ray mentioned, once in several years. And remember that fault-induced islands are not going to occur except in corner cases, which can be screened. And we go into a lot more detail about that in the paper. Reactive power balance must exist at the moment the manual switching occurs. And Ray showed that this balance condition only occurs for several hours a year. The third, active anti-islanding has to fail to detect the island in order for it to persist. And without all these things happening simultaneously, you won't see a persistent island. So quite a few things, confluence of events needs to occur. As Ray mentioned, that's the first two of those, just having the switching event overlapping with the reactive power balance is only likely to occur on the order of thousands of years. And then you also need to have anti-islanding fail at that time. So without all those things happening, you won't see the persistent island. If an island does happen to occur, because these are manually switched islands, then the utility practice to check that the line was de-energized after they switch the line off, knowing that there's DER on it, they can ensure that there are no issues and the island does not persist. So if the island does occur, then they can take corrective action, like turning off a large DER. And oftentimes large DER have communications to, say, a recloser that can switch the DER off as commanded by the utility. And that would likely be enough to basically unbalance the island and cause it to extinguish. And in the unlikely scenario that you have lots of small DER contributing to a persistent island and all their active anti-islanding has failed, then you might have to turn off a few of them or take some other switching measures to turn them off. But so far, we don't know that this has really been an issue that actually needs to be done on any kind of regular basis whatsoever. So now moving on to what would happen if all those previous things did happen to occur and you wind up with persistent islands. So again, you've got the manual switching happens, you have the reactive power balanced very tightly, and anti-islanding has failed. And perhaps before the utility personnel extinguish the island by turning off a DER or taking other measures, then first, as Shay described, damage to customer and utility equipment won't occur because generally your power quality is not going to get so bad. And if it does, then the inverters will trip on protective settings and extinguish the island. And so you might have loads being fed for a little bit longer than they normally would be, which actually keeps the customer loads on. But they're not going to cause damage to those loads or to the utility equipment that's on that island at the same time. Also, ground fault overvoltage won't occur because it's been mitigated by load or taken care of via a grounding bank if there's not enough Y-connected load. And that can be done in the interconnection process where you can identify, okay, is there enough grounded load? And I'll make a little plug for our model interconnection procedures where we have a supplemental review grounding screen that can take a look at inverters and rotating machines separately. And the utility can assess whether that grounded load does in fact ensure effective grounding for the inverter. And then if not, of course, that smallish grounding bank that is resistively grounded can be used in lieu of what is normally required today, which are larger grounding banks that specified in the terms of rotating machine parameters. And so even if you happen to encounter a circuit that doesn't have that much Y-connected load to ensure effective grounding, then the grounding bank that would be required for the developer to install would actually be much lower cost than what is typically required today. Then load rejection overvoltage is not going to occur because inverters are just certified to not cause it. So we've taken care of the main overvoltage issues, which could be a consequence of switching. And so if unintentional islanding does happen, once in thousands of years on a feeder and the anti-islanding fails, there will actually be little consequence. So, our conclusion about this is that DTT and other mitigations are not needed because there's nothing that needs protecting against. So our overall conclusions are that if you're worried about anti-islanding failing and having even inconsequential islands occur every few thousand years on a feeder, then some practical screens can be put into place to ensure anti-islanding protection does not fail. And some utilities like PG&E in California, National Grid on the East Coast have started to, employ those types of screens that look at the anti-islanding methods. And, they're already, so these methods of screening are apparently, able to be done already. They certainly are more complex than the basic penetration screening processes that we started out with and that some utilities still employ today. But we think it is worth it to avoid the application of mitigations where they're likely unnecessary. So that means direct transfer chip is just simply unnecessary for inverter DERs broadly, although it would still be used for rotating machines. And if you recall, if we have inverters coupled with rotating machines, then as long as we're keeping rotating machines to a lower percentage of the island, then that will ensure that the anti-islanding remains effective. If all of your rotating machines have DTT, then you're not even going to encounter those scenarios. So even further mitigations like reclose blocking could be avoided as well. And as we didn't go into too much detail in it, but that was, basically due to, Ray went over how faults aren't going to cause an island, and so therefore you're not going to wind up with reclose scenarios that are reclosing back into an island. And that is actually a less expensive mitigation than DTT, but per the report's findings, that is also even unnecessary and could be mitigated through screening as well. So regulators, have often taken a hands-off approach to technical requirements and really left the utilities to determine a lot of the technical specifications, including if and how DTT mitigations are arrived at. However, that's really led to some overly conservative and expensive application of those mitigations. And it really varies across the country. A lot of utilities have had a lot of success avoiding the application of DTT through today's screening practices, which we think could be advanced even further. So regulators can really ensure that new technologies are incorporated into those technical requirements with the application of new research to ensure that the requirements are right-sized to the risk. Generally, the utilities aren't going to want to take on any level of risk with the DER but they may be kind of overcompensating for that risk with these expensive mitigations. And so we think there's a role for regulators to play and for other stakeholders to have an input into what those technical requirements are and ensure that any of the most recent research can be relied upon. So there's a lot more technical detail in the report, as I mentioned, but we've tried to summarize the main points for non-engineers in the executive summary, which is several pages long. The whole report is around 60 pages. So there's a lot of technical detail around all the assertions, such as, the power balance and whatnot that Ray went into in terms of coming to those numbers. And we'd love for you to read it. You can find the report at this location on our website, or go to our website and look under the resources tab. So we really appreciate y'all joining us today. And now I think we'll try to address some of the questions in the final minutes here.
Thanks, Brian. Looks like our top upvoted question right now is who has the authority to decide the level of unintentional islanding risk that is acceptable? And how does one decide the acceptable risk threshold?
Yeah, I think that's an interesting question. I think that really goes to our call to action for regulators. Really the utilities have to deal with the risk, right? And they do deal with risk on a regular basis. When it comes to serving load, they deal with risk. There's certainly risk inherent in the electric system, right? The question is just, what does that balance look like when we're talking about DER interconnected, that the utility is not really supplying that energy, but they're still on the hook for requiring the safety and reliability and power quality of the system. And so I think that's where regulators have to step in and say, what is that balance? And we can't say exactly for sure, but we think we can maintain high levels of safety and reliability while not being overly conservative and not overburdening DER projects with lots of protection. I mean, we could go on and on with layers of protection to avoid any risk whatsoever. But one of the reasons for putting out this report is to really compile all the research that's been done in the past and try to figure out, what are the scenarios in which extra protection is really warranted. Anybody else have something to add there? If not, let's go on to the next question here.
All right. One other question we've gotten is, we are seeing increased number of the residential BESSs, or battery energy storage systems, with backing up capability, in parentheses, grid forming inverter based. What will be their impact on the large inverter based DER's anti-islanding protection?
Yeah, I don't know if anybody else wants to weigh in here, but my answer to that would be that they are inverter-based DERs themselves and have the same types of anti-islanding protections that are required of other inverter-based DERs. So they're going to be UL 1741 SB certified. They're going to have to follow all of the all of the IEEE 1547 requirements. And so basically all of the things related to mixing algorithms and whatnot that applies to energy storage based inverters as well. If they have backup capability, that backup capability is generally only being utilized when in backup mode. So they are not in the grid forming mode when they're attached to the island operating in parallel. So they would be operating in grid following mode and yeah, not really affecting the islanded circuit any differently than any other inverter-based island. And they use that grid forming capability once they switch over and disconnect from the grid. And that's, that's basically the point of having them, is to provide backup power when the power goes out. So they would also have to have the anti-islanding capabilities in there. If they detect anti-islanding, then they would likely go into the backup mode. But they're not going to, as far as we know, not going to cause further issues. There could be, if there's ever a high penetration of grid forming inverters on the distribution system, then we might have to take a look to see what differences there may be in terms of how those interact with other inverters. But that hasn't happened yet. We're likely years away from that even potentially being an issue. And other than being in microgrid mode, there's not necessarily a use case at the moment for having grid forming inverters on the distribution system that I know of. Anything to add, Ray or Shay?
No, you kind of beat me to it. I turned my sound and camera on because I was going to add in about the fact that grid forming inverters generally stay in grid following mode unless they're in the microgrid mode of operation, separated. I see the last question entered in here, and it's got 2 upvotes. I think that might be a good one to take on next.
Sounds good. We have the question, do you recommend not to perform islanding screening as well if the risk is low, regardless?
So I might have to come up with a personal opinion on the fly here. We don't necessarily make the recommendation in the report that you should not screen, but it does seem that there is very little risk involved if you don't screen. But if you are worried about those likely inconsequential islands happening from manual switching every 1,000 so years, then you could screen, be conservative. I think it's, we're talking about taking, a little step away from being overly conservative. So I wouldn't necessarily say throw out the screening practices. I would say, if we implement those screening practices, that's likely to get utilities more comfortable with taking on any level of risk, because we could see that risk is further mitigated, by the screening. And so the screening, adds a slight level of complexity to the interconnection process, perhaps, and the evaluation that's done at the utility. We wouldn't recommend against it. But it does seem that, even without that, it's a very low risk. The islands that could potentially occur are very low risk.
With the exception of certain situations, for example, if there are significant amount of synchronous generators on the circuit that don't have DTT is one exception where I think it's important probably still to do the screening.
Right.
And the other might be a circuit that you frequently drop as a matter of practice. I think that's pretty rare, but you might have a circuit that you move between sources and the sources have a big phase difference in them, and that you have to do a cold transition or a open transition, moving the circuit from one source to another. I think utilities avoid this because it blinks out customers. But if you did have a circuit that you're doing that frequently, and obviously we'd want to take a closer look. But I think in general, it's sort of fruitless because, I mean, what will it really tell you? You do the screening and we've pretty much made the case that even if you had DR capacity far in excess of the minimum load, even exceeding the maximum load on the circuit, that risk is really, really small unless you have synchronous generators on the circuit or you're dropping the circuit a lot.
Thanks, Ray. Thanks, Brian. Looks like we are at time. So if anyone has any additional questions, Brian and Shay's contact information is here. And we really thank you all for joining us today. And before we wrap up, I will just note that if you appreciate the work that IREC is doing, there are a number of different ways that you can support our work. And although we are largely foundation and government funded, support from individuals like you makes a huge difference to our ability to implement our work. So you can support our work directly. There's a QR code here to make a donation if you're so inclined. And there's also other opportunities to support our work, such as connecting us with corporate sponsors or letting us know about clean energy barriers in your community, so that we can prioritize those for intervention. So thank you all so much for your time and your participation today. And with that, we will wrap up and we will send you the slides and the recording in the next few days. Thank you.